Welcome back, chemistry fans. Today we're going to deal with our last new topic in this unit 2, talking about how things bond together. We've already talked about how to name a molecule. We've talked about how to draw a two-dimensional shape of molecules, and we would say that that's the Lewis structure. And then we started to put it three-dimensionally. We popped it up and made it into one of 5 different possibilities: linear, bent, trigonal pyramid, trigonal planar, and tetrahedral. And now what we need to do is figure out what happens if they have the same structure, same number of atoms, but they have different structures. What's going to cause the linear to be linear or the bent to be bent? Why does one molecule want to be bent, one does be linear? Well, we know from the Lewis structure it has to do with those extra electrons. But because it's bent, something unique is going to happen. It's going to start to develop something called polarity, and that's what we need to talk about today. So let's share the screen and let's get into what polarity is. So polarity, as you can see in this diagram, has to do with some new symbols. And it has to do specifically with this water molecule. It's a perfect example. What we can see in this molecule are these arrows. Well, those arrows are pointing towards where the density, the majority of electrons are located. I would like for you to notice that the oxygen is bigger than the little hydrogens, and that in itself causes there to be a higher density of electrons on one half of this molecule. Also, the fact that the hydrogens are on one side of the molecule, they're not evenly distributed, not symmetrical, also causes there to be one side lopsided with more electrons. Now, those little squiggly Ds with pluses and minuses, we'll talk about those as being dipole moments here in just a second. All right, so what I need you to look at here and notice about polarity is that it is an unequal sharing of electrons. And this is caused by either its shape or by its size. So if we look at these examples that are here, you will notice on the polar side, what I have are 2 specific molecules that are always going to be polar. I have on the left the bent molecule, which is the second one. And I have the trigonal pyramid. Those 2 molecules are always going to be polar because they have these extra electrons, which cause repulsion, which cause the molecule to bend, which means it's not symmetrical, which means that a majority of the time the electrons are going to be in one location versus the other location. Now, in the top one, it is linear, and linear in of itself is not polar, but because of the vast difference in size, there is going to be more time that the electrons spend on the large atom than there is on the smaller atom. And you're saying, well, why is that the case? It's just a matter that it takes longer to go around to orbit a larger planet, a larger atom, than it would for a satellite to go around a small planet. Okay. So now on the right side, the nonpolars, what you should notice is they're symmetrical. They're quite even going around. And even though that this tetrahedral down here on the bottom does not look symmetrical, in fact, every single angle, it's just the way it's drawn, it's difficult to show it, is 109 degrees. Every single one of those is going to be split evenly into 109 degrees. And you're saying, well, why isn't it 100 or 90 degrees? It's just the way it works out. They're all 109 going around in this 3-dimensional shape. And so what that means is they evenly share their electrons. So it will be non-polar by that definition, because polarity is an unequal sharing of electrons. So let's talk about the 2 in specific ways in which polarity can develop. First one we've already talked about. We've talked about both. The first one is the size. So notice here what happens is, because fluorine is larger, it will take, if I had a stopwatch, it would take longer for an electron to go around the fluorine than it would to go around the hydrogen. And because of that shorter distance in time, we are going to develop a temporary negative charge. based on its size. We're going to develop a temporary positive charge because all electrons are negative. So the longer it stays on one side, the more negative that side becomes. The shorter time would have a positive charge. Now, this is reflected in these two different symbols, the squiggly D and the squiggly D with a positive or negative if it's got the electrons. Notice there's also an arrow being shown here, and it's pointing towards the negative side, and there is this positive symbol that is kind of being made on the other side. So positive points towards the negative. And we call this temporary magnetic charge a dipole moment. And so let me go ahead and jump into that. Dipole moments. These are the symbols that we need to show on a molecule so that you understand, prove that you understand that there is not equal sharing, that there is polarity, and it can be reflected in both ways or one of the two ways. You need to have those squiggly Ds, which represent a differential. They represent a delta, if you will. This is a lowercase delta. And so it's just like in your math classes, whenever we did the formula for slope, it was delta y over delta x equals slope. Well, we're just using a lowercase delta in these cases to represent the difference in the electron sharing. And these are called dipole moments, either with the arrow pointing towards the negative with a positive symbol on the other side, or with the squiggly Ds. Okay, now back to the story. So if we have, though, an understanding of why size causes polarity, well, we need to be able to predict that. And we already know the trend for atomic size. We know that the largest element on the periodic table is francium, down here in the bottom left corner. We know that the smallest element is somewhere up here in the right-hand corner, whether that be fluorine or helium, whichever you want to say, or even hydrogen, but that doesn't seem to fit the trend. So we generally speak in terms of top right going down to the bottom left. If you wish to talk about hydrogen, and that's the most accurate, smallest element, just make sure you understand the trend. So whenever we compare atoms, so that you would know which size is smaller and larger, so you can tell me where the polarity is, you will be able to show me on this periodic table, or you would be able to predict their polarity then. Okay, moving on now to the second trend for describing polarity. And I believe yesterday I put in a different symbol here, a different image here. I'm going to do the same thing today. Image, this is the one that I want right here because it'll be easier for us to write it onto here. So hang tight while I add this in. Okay, so polarity also can be caused by the shape of molecules. The shape of the molecule is not sharing electrons equally based on the fact that there are extra electrons in certain molecules, which cause it to repel, push on the bonding electrons of the rest of the molecule, causing it to bend. Because of that chevron bent nature of the molecule, you will notice that it is not symmetrical. There are more atoms on the bottom half than there are on the top half. Well, that causes a polarity. Now, this polarity up here would have fewer electrons, and there would tend to be more electrons down on the bottom. Now, there could be a case where, though, the atom is so much larger in the center that it causes the electrons to be on the top. But generally speaking, we have polarity. You just kind of have to combine the two terms and understand that if one, the size is polar, or if the shape is polar, it doesn't matter which it is. If one of the two is polar, the entire molecule is polar. If neither of these are the case, if I have linear and all of the atoms seem to be about the same size, you are non-polar. So polarity occurs whenever we have unequal sharing of electrons based on size or based on shape. Now, we need to be able to understand what shapes are polar. So let's move this image over here and we can talk about those. If you have extra electrons, you are not only going to bend the molecule, but you are also a polar molecule based on shape alone. So the trigonal pyramid or the bent, they are always polar molecules. So if you can draw your Lewis structure and you can tell me then what its Vicepar shape is, you can tell me that it is bent trigonal, you could tell me that it is polar. We could then refer to its size and also get that detail later. All right. Well, now that we understand that detail, what we need to do next is get into a mathematical way to prove that it is polar. This is going to be our second trend on the periodic table. What you will notice is that this trend tends to be the opposite of what it was for atomic radius. On atomic radius, the biggest element was down in the bottom left corner with francium. Now we have the opposite. We have the largest element being fluorine. That's why I was trying to encourage you to memorize just two elements. Francium's the largest size. Fluorine has the smallest size. Fluorine now has the largest electronegativity, and francium has the lowest electronegativity. What is electronegativity? Electronegativity is a numerical representation of polarity. It is how well you steal electrons. If you want an electron, you are going to be more polar because you are taking the electrons. Again, polarity is an unequal sharing of electrons. So as we move through this detail, electronegativity, here is an image. Chlorine is a bigger atom and it wants the electrons more, so it has a higher electronegativity than does hydrogen. Because of that, we create polarity. So here are that trend again without the values. I must give you a periodic table that has the electronegativity values. For us to determine if a molecule is polar or not based on mathematical analysis, we must have that table and we must then apply the values in a difference. So we must, sorry, that's not on here, so it's on the next slide. We must subtract the two values. Now, why does fluorine have the largest electronegativity compared to some of the other elements? It's because fluorine does not have a stable octet yet, but it still desires one. It has 7 valence electrons. Well, that's very close to a stable octet, but it doesn't have that yet. And if I compare it to then francium, francium already has 6, well, it has 5 stable octets, but it has 6 completed rings. It is not interested, it doesn't necessarily need a 7th completed ring, so it is not interested in stealing anyone else's electrons. In fact, it's the opposite. It's willing to give its electrons. So the closer you are to a stable octet, the more likely you are to steal electrons. The lower you are on the periodic table, the less likely you are to steal it. What this then leads us to is the calculation between the difference of the two electronegative values. We call the difference, the value that we calculate, the ionic character. The larger the ionic character, the more polar it is. In this, they list it as ionic, but it would be called polar. The closer the two elements are on the periodic table, the less the difference in their size, the more likely they are to share their electrons, making them non-polar. If they're somewhere in the middle, it's going to be polar covalent. Now, what's the break apart? Where do we get the dividing line? It's somewhere here at 0.4. If you are between 0.4 and 2, you are polar covalent. If you are very small in difference, you're non-polar. If you're very large in the difference between your numbers, you are polar. So the best way to learn about this is to practice this. So let's jump into the examples that we have. Carbon and fluorine. let's find out what is the difference in their two values. So on this periodic table of electronegative values, carbon is a 2.55 and fluorine is a 3.98. Now, this is always going to be absolute value, so it does not matter how you subtract the two values. You end up with a positive value no matter what. So 3.98 minus 2.55, and you get 1.43. So let's go back to the ionic character and figure out what type of bond is between those two. 1.43 puts it smack dab in the middle, meaning that this is sort of polar, but not real polar. So it's a 1.43, meaning it is polar covalent. All right, let's try another one here. So the last one, sodium and fluorine. So if I look on this chart, sodium and fluorine. So fluorine we already know is 3.98. Sodium is 0.93. If we subtract those, I get 3.05. That's a large difference between these two atoms. So now we can determine what type of bond this one is. If it's really large, 3.08, that was definitely polar. That is a polar molecule, ionic, if you will. Okay. This is everything that I wish to share with you. You now have mathematical ways to prove polarity. You have definition, shape, and size that you can define and identify polarity. And we need to understand polarity is an unequal sharing of electrons. Thank you very much for your time. Talk to you again soon. Bye-bye.